Welcome to Pharma Drama, the channel where we look at the science of healthcare and healthcare products. In this video, I want to explain a type of material that is really important in making medicines work effectively: amorphous materials. So, if you're ready to understand them, put the kettle on, sit back, and let's make a start. I think we should start with the actual definition of the word amorphous, which is lack of form. Remember, nearly all materials, unless they are pure elements, are made up of molecules. So when we think of their physical form or state, we should actually think about how the molecules are packed together. There is only one physical form in which the molecules in a material are neatly arranged into a repeating pattern: the crystalline state. Because all the molecules in a crystalline solid are aligned, we say there is long-range order. In any other physical form, the molecules are randomly arranged. This includes liquids, gases, and amorphous solids. So the basic definition of an amorphous material, at least in the world of pharmaceuticals, is a material in which the molecules do not have any sort of long-range order. Now you might say to me, okay, in that case, what is the difference between a liquid and an amorphous solid? Surely they are the same, as they both contain molecules that are randomly arranged. And I would agree, if the only thing we cared about was the arrangement of molecules, or lack thereof, they are in fact the same. And considering a liquid and an amorphous solid as being more or less the same thing is actually very useful when understanding amorphous solids, as I shall discuss in a moment. There is, however, one important difference between an amorphous solid and a liquid: viscosity. Viscosity is a measure of the resistance to flow. The higher the viscosity, the harder it is to make a material flow. Usually the viscosity of a liquid is low, which is why liquids flow very easily. The viscosity of an amorphous solid is, on the other hand, high. High enough that when you apply a force to it, it does not flow like a liquid, although it may deform. So if you think of an amorphous solid as a high viscosity liquid, I reckon you'll be able to understand pretty much all of their characteristics. Let me show you why amorphous materials are important in medicine. In my hands, I have two things: a sugar cube and some candy floss. They look very different, don't they? The sugar cube is quite hard and dense, while the candy floss is light and fluffy. What molecules are these two materials made of? I'll give you a moment to think about that. Have a think. Got an answer? The answer is sucrose. They are both made of sucrose. The only difference between them is how the sucrose molecules are packed together. In a sugar cube, the sucrose molecules are aligned in a repeating pattern and the material is crystalline. Whereas in candy floss, the sucrose molecules are randomly arranged and the material is amorphous, or a high viscosity liquid. Let's think about what this means. The chemistry of the materials is the same. They are both sucrose, remember, but their physical properties are different. Consider what happens when we add them to water. Imagine you're making a cup of tea, like I suggested at the start of the video, and you take sugar in your tea. You add sugar to the hot water, and then what do? You stir. The reason is that in a sugar cube, the sucrose molecules are closely aligned, and they interact with each other. You have to put energy in to break these interactions before the sucrose molecules can break away and dissolve, and this takes time. Stirring adds mechanical energy and helps speed the process up. What happens when we add candy floss to water? It instantly dissolves. Why? Because the molecules are randomly arranged, and so the strength of any interactions between them is much less. Therefore, much less energy is needed to break the molecules apart, and so dissolution is much more rapid. Really, we are just mixing two liquids of different viscosities. One further important point is that because amorphous solids are really just high viscosity liquids, they don't have a melting point. There is no crystal structure to break apart. It really confuses people. As you heat an amorphous solid, it will eventually turn to a liquid, so it appears to melt. But it never does. As the temperature increases, the viscosity of the material reduces, and eventually it will reduce enough that it flows readily. Now think what this means for a medicine. Many medicines are taken orally, tablets and capsules for instance. The patient swallows the medicine, and then what needs to happen for it to have an effect? It needs to dissolve. No drug can be absorbed and act in the body without first being in solution. If you swallow a medicine containing a crystalline drug, it will dissolve much more slowly than if you swallow an amorphous medicine. Remember, you can't stick a spoon down your throat and stir a medicine like you can a sugar cube in a cup of tea. When a medicine needs to be fast acting, making it an amorphous solid is a very effective formulation approach. It should not surprise you to know that amorphous materials are way more complicated than I've had time to explain here. I just wanted to give you a basic definition and give you an example of why they are important in medicine. We'll discuss amorphous materials in much greater detail in other videos, but for now, if you remember that an amorphous solid is really a high viscosity liquid, then you'll be well placed to understand them. Right, I hope you found that brief description useful. If you did, please hit the like button and consider subscribing. It really helps the channel. I will be posting many videos explaining fundamental science concepts, and if there are any particular topics you'd like me to explain, please leave a comment below. Otherwise, thank you so much for watching, and I'll see you again soon.